Hey, Joshua.
Hey, Adam.
How are you?
Good, good. How are you?
Good.
How are the meetings in the morning? Are they going well?
Great. Yeah, that's great.
Mhm.
Yeah. Um, yeah. I mean, I feel like overall, uh, this way of doing visits is like not as terrible as I think people were worried
Yeah,
they might be.
yeah.
um,
Apparently, this is the only way we can do now. But yeah, uh,
um, but yeah. Should I test my screen
yeah,
sharing?
sure. Yeah, yeah. You can test that first. Yeah.
Give me 1 second here. Sorry. Sorry, I'm just trying to deal with. I have like a
Right,
million.
take your time. Yeah.
Sorry, 1 second. Something weird's going on with my laptop. Oh, okay. It's funny. I was like, the screen it was showing to share was this PowerPoint presentation, but for some
Mhm.
reason it was showing a different slide of it. So I thought it was a different version of the talk, which I didn't want to accidentally put up the wrong version.
Yeah.
uh,
Oh, I think this is good. Yeah.
is
I
this
see
the
it.
right screen?
Yep.
Okay. Um, Let me just see if do actually. Um, so is this now showing the right thing for you or no?
But it's actually also showing the next slide and all this other information.
I see. Okay.
Yeah.
Now is it good?
Yeah. Now it's good. Yeah.
And you can see this now.
Yep. I can see the mouse as well. Yeah. So this is good. Yeah. Are you busy this semester? You have to teach courses as well?
I'm not teaching this semester, but especially with admissions this year, it's just been incredibly busy. Especially the past month and a half. I feel like I've maybe been the most busy that I've been so far here. It's been a little bit exhausting, but
And how's the lab going with the COVID situation? Is it running 100% right now?
yeah, more or less. Yeah, I mean, it's definitely like a different situation, but in some ways, I feel like because we were forced to, the group is running probably more, the experiments are running more efficiently. Like we're in a staggered schedule, so we're running 7 days a week. And I think certain things that might not have happened otherwise have happened. And just in terms of like people being like, okay, like I really need to learn how to do this thing because I'm not going to be working with someone else while doing it and stuff like that. So it's overall, it's been good. Yeah.
And how many students you have now?
I have three. So I have
Oh, okay.
two
And
on
you have
the.
postdocs as well, right?
Yeah, so there are two on the two students on the Strontium project and one in the Ytterbium project, although I just hired another person, but he's not here yet. And then a postdoc on each of those.
You have been very productive in, in the past years. I saw you have very, quite a few very high profile papers.
Thanks a lot. Um, uh, I've definitely, benefited a lot from being at JILA where there's like a ton of stuff for getting off the ground
Yeah,
quick.
yeah,
Um, I'm just gonna take 1 second to look at my talk. I just want to see one thing.
sure, yeah.
Oops. It's weird, right? Um, there we go. Okay. Oh, I see the problem. seems okay. All right. I got nervous for a moment. There really was something that, because my computer crashed earlier, so like all this stuff I was a little nervous about, but it seems fine. Good.
So is JILA also doing colloquium remotely like this?
Yeah, sort of. I mean, so the physics department is, but we had this quantum seminar series out of Qubit. That stopped, and we'll start that back up, I think, in the fall.
Yeah, I remember at some point you organized this AMO seminar, right?
Yeah, that's that. Yeah.
Okay, so that stopped. Okay.
Yeah.
Okay.
Yeah.
But I guess things will get back to normal pretty soon, right? Hopefully.
Yeah, it seems that way. Although I don't know. Seems
Are the
increasingly
students doing well on campus?
Starting from square one. What'd you say?
Are the students doing well on campus at CU Boulder this semester?
You mean like the COVID?
The cases, yeah.
As far as I know, the COVID situation has not spiked. So I guess I haven't actually looked at the like CU COVID counter in a little bit. Maybe I should. But last year was obviously not ideal.
Yeah, last fall I heard it's pretty bad there.
Yeah, it was not good.
Yeah, but you don't have to teach, so that's good.
Yeah. I was teaching when it started. So that was, I mean, as for everyone, a pretty abrupt transition. But
I have to teach 2 courses this semester, but they're remote, so I'm okay.
Yeah. What are you teaching?
So I'm teaching an undergraduate quantum mechanics and also a graduate quantum antibody physics. So that's actually a new course. Yeah.
Cool.
So we recently started this quantum engineering master's program, and a few new courses. Yeah.
Cool.
Yeah, we're also trying to hire a few more quantum information people in the next couple of years.
Oh, cool.
Yeah.
Cool. So these are all recorded, it looks like?
Yeah, so these are all recorded. And we have about 50 students registered in this colloquium course. So there's actually a course associated with the colloquium, and the graduate student are required to basically attend the colloquium. And we'll even take attendance of the students, but that's automatically done by Zoom. So there's like a there's like a report you can generate.
Yeah. Got it.
Yeah, we also have some faculty joining the colloquium as well, but most of them are students.
I see. Okay, cool. Hi, Dan.
Hello.
Hi, Chip.
How's it going, Joshwan?
Good. How are you?
Good. So, Adam, your talk is very well timed. I'm teaching graduate E&M.
Oh, cool.
We're going to be talking about stress tensor and forces, trapping forces and stuff.
Oh, okay, cool. I feel like a lot of the E&M in these experiments is actually like pitifully basic. We like turn on some current in a coil and it makes a magnetic field, and we're happy if it's stable. And like,
oh, sure, yeah.
But
I was thinking more in terms of like optical tweezers and stuff.
Yeah, no, that's true too. I just sometimes I think about how I struggled, late at night doing Jackson sets in grad school, and how little of that actually has impacted anything that I do now. Maybe I shouldn't be saying that to like a colloquium full of graduate and undergraduate students.
Yeah,
it's a lie. I take it all back.
Okay, I think we can get started. It's already 4. So let me first introduce our speaker today, Dr. Adam Kaufman. So Adam is an associate JILA fellow and assistant professor at CU Boulder. So he did his PhD at JILA, studying full-body quantum mechanics of atoms in optical tweezers. After that, he was a postdoc fellow at Harvard, so where he investigated the dynamics of entanglement in thermalizing many-body systems and other Bose-Hubbard phenomena. So in 2017, he moved back to JILA, where he has continued working in the field of quantum science with neutral atoms. So he's a winner of the prestigious APS Damop Thesis Prize in 2016, and he recently pioneered the research on atomic clocks based on optical tweezers. So with that, let's welcome our speaker, Adam, today.
Thanks so much for the introduction. It was great having all these meetings this morning. I have to say that I think I mentioned this in one of the discussions, that it's nice that of all the talks that I've had to give, this one at least is not like a flight that's averted. It's just a car ride. So hopefully in the future I can come in person and we can chat in labs and things like that. Okay, good. So thank you for the invitation to speak here. So I'll be telling you about work that we've been doing over the past couple of years using optical tweezer arrays of neutral atoms for metrology. So just briefly before I dive in here, I just want to describe the team. So there are actually 2 experiments in my lab, and I'm really going to be focusing on this one that focuses on strontium atoms. And this work has really been a growing collaboration with the Yi group at JILA, where we've learned a lot from them about atomic clocks, and further been able to collaborate with them on their technology for making really narrow lasers, which allows us to understand our systems much better. Good. All right, so the work that we do in my group broadly falls into this really accelerating area of quantum science, which simply put, I might describe as the direction which seeks to use quantum mechanics to perform tasks that are not possible with classical resources alone. So to just emphasize a couple areas where this is prominent, so this can be used for things like quantum communication, where information can be sent from one party to another in a nearly perfectly secure fashion. This can be used for tasks known as quantum simulation, where something that's computationally too difficult to solve on a classical computer, we can use a quantum system that we can control well to learn about. Furthermore, for tasks like quantum computing, which can allow for, say, breaking of RSA encryption, this is a phenomenon which is made possible by peculiar features of quantum mechanics. And finally, and this is more the, I should need to fix something with my Zoom window here. It's not working right. Sorry, I just won't fix that. Quantum science can also enable new directions in metrology. So, sorry, I'm actually really having an issue here. Let me just fix this. Sorry, it's just my Zoom window is covering half of my slide, and the laser pointer is not allowing me to click on it to move it. Okay, there we go. Sorry, everyone. Okay, so to enable tasks like this in quantum science, it's natural to ask sort of what are the things that we need to do these things. So to highlight 2 areas where I think there's a lot of ongoing work. One is microscopic control and detection of a quantum system, by which I mean to be able to control and detect individual quantum objects like an atom. Another area is developing scalable quantum coherence, that is having many identical long-lived quantum objects, in that case, qubits. So one doesn't need both of these things at the same time in order to perform interesting tasks in quantum science. For instance, for doing quantum communication, where you're sending bits of information over long distances, you might only need a couple of qubits and really high fidelity detection of those qubits. On the other hand, for areas like metrology, you might not need to individually detect all of the qubits in some large system. You just need to measure aggregate information about that system, but the qubits that comprise that quantum system need to be really long-lived. Then there are tasks like quantum information and quantum simulation, which really benefit and leverage the ability to have both of these things at the same time. So a key theme of this talk is looking at how, by combining both of these capabilities for metrology, we can really enable new directions and do new things. So to sort of extrapolate a bit further on this idea of a quantum science wish list of the things that we need, there's the stuff that I already said, multiple quantum objects that can be long-lived, that we have single particle detection of, and furthermore, that we might be able to deterministically prepare, that is, with really high fidelity, prepare them in a particular state quite often. Let me add to that the ability to engineer strong interactions between the qubits. This is important because it means that you can really explore the full Hilbert space of states that's possible with a given set of qubits. Amazingly, these days, there are a large number of different experimental platforms which are all beginning to combine all of these features in novel ways, ranging from various atomic and trapped ion systems, such as those in Boulder and at NIST, as well as molecules, to things like superconducting qubits, which are Google and IBM have now made famous, as well as D-Wave, and further things like NV centers in Diamond. So this talk really focuses on this particular platform of atoms and optical tweezer arrays, which you know, I'm certainly not going to say that one platform is better than all the rest, but one thing that's super nice about this platform is it's able to combine a lot of these capabilities in a very simple way. So simply put, this experimental platform can be described as follows. By shining light into a microscope objective, so this is a schematic representation of just a microscope, and shining it into an ultra-high vacuum chamber, so this window here is meant to represent the window of the vacuum chamber, the individual foci of light that go through this microscope form so-called optical tweezers and can trap individual single atoms. So these pictures here correspond to pictures of those single atoms that we can actually make with the same objective used to make the tweezers. And this is an averaged image. So this is taking many runs of our experiment and just showing over and over again that we have these single atoms. And what's great is right off the bat, this gives you single particle detection and control of individual atoms, which was part of that list that I was telling you about a little while ago. And it just, all of these things are combined in a very simple package. Okay, so because of this simplicity paired with a high degree of control, there's been a lot of progress in recent years for directions such as preparing scalable and tunable systems of atoms. So these are pictures from the Brouwer group in France, where they can rearrange arrays of atoms into nearly arbitrary distributions using the fact that you can move the tweezers around while they're trapping the atoms. These systems also can be used for measuring exotic observables like correlation functions in large arrays. Furthermore, a very important feature, which is often sort of less emphasized, but I think is actually perhaps one of the most important things, is that these experiments are really high duty cycle. That is, you can run them very quickly and therefore acquire precision very quickly. This is useful for, say, if you're doing a quantum simulation and you need to measure quantities that are, say, very close to zero, but just barely above zero, something like that, or for directions like metrology, as I'll discuss. Excuse me. Finally, importantly, these atoms, when they're trapped in tweezers, can be made to interact in various ways, such as by overlapping the tweezers and thereby the atoms in space and allowing them to collide. This realizes so-called exchange interactions. Furthermore, if the atoms are pinned in space, they can be made to exhibit long-range interactions through so-called Rydberg excitation. So it looks like there might be a question. Should I answer them as I go? How do you want to do questions?
Yes, I usually will read out the question and then you can answer it. So there's a question from Nick. He's saying, what is the typical duty cycle for these systems in Hertz?
In Hertz? So for this experiment here, it can be anywhere from 2 to 5 Hertz, which should be compared with cycle times in cold atom experiments with similar capabilities, where it can have a cycle time of a minute or 30 seconds. So this is a factor of 100 acceleration over, like this technology enabled a factor of 100 acceleration in what's possible with these systems. But it's still a lot slower than, say, a superconducting qubit system. Does that answer the question?
Yeah, that's good for me.
I guess there won't be communication here. Yeah, okay, got it. Good. So because of this novel suite of capabilities, these systems have been used for a lot of important directions in quantum science. So for instance, single qubit gates and 2 qubit gates are now showing Fidelity is above 95%. The single qubit gates are actually really quite good at 99.8%. So this is not quite there, but close to the level of so-called fault tolerance, where ideas like error correction might save quantum systems from exponential scaling problems. Furthermore, these systems have been used for few to many body physics. So we're looking at things like few body Hubbard physics, transverse Ising spin models, non-equilibrium phenomena, topological phenomena, fundamental studies of entanglement. So they've really been just quite versatile. So in recent years, one question has been, could this tool set be expanded to different kinds of atoms? So a lot of the work so far had focused on so-called alkali atoms, which have a single electron in their valence shell, which is great for laser cooling, but it doesn't exhaust the set of things that one might be able to do with cold atoms. So for instance, in really beautiful work at the CUA at Harvard, there's been a collaboration looking at trapping molecules in tweezers whose internal degrees of freedom and interactions could enable new directions. In my group, and also at Caltech and at Princeton, and the Andres group and the Thompson group, we've been looking at trapping alkaline-earth atoms, which are atoms with 2 electrons in their valence shell. So these are supposed to represent the little electrons whizzing around the atom. And actually, I should mention to you that there are a lot of groups exploring this technology now too. So this will really be the focus of my talk. Why would someone want to explore this alkaline-earth atom? This might seem a little bit boring or mundane, but the fact of the matter is that the main reason is that these atoms have more transitions in them that you can control. So for instance, there's this transition which we call the imaging transition, which allows us to do high fidelity, high resolution imaging of the single atoms. So this goes back to this thing I was talking about at the beginning about what we want for quantum science. This is a nice tool for doing just that. In addition, there's this narrow cooling transition, narrow in the sense that the line width of the transition is narrow, that is just longer lived than this transition up here. And that actually allows us to do so-called ground state cooling. That is, if we have single atoms in our tweezer, we can use this transition to cool the atoms all the way to the mechanical ground state of the tweezer itself. Furthermore, and this will be really an emphasis of this talk, these alkaline-earth atoms, independent of any of the tweezer stuff that I'll be talking about, are really famous for their use in metrology because of this transition known as, unsurprisingly, the clock transition. And the key feature of this transition that makes it so important for metrology is that if you view this transition as an oscillator, that is, that when I put an atom in a superposition of these 2 states, the electron is jiggling around like an oscillator. Those oscillations are occurring at an optical frequency, so say hundreds of terahertz, but ring down over a time scale of hundreds of seconds. So this corresponds to a quality factor that's absurdly high and really enables new directions in metrology that I'll talk about.
So Adam, can I ask a question here? So you mentioned about this ground state cooling. So do you do sideband cooling or EIT cooling here?
We use resolved sideband cooling.
Okay, but is that efficient enough? Like you have to do it for a
in the
long
sense
time.
like what the temperature of the atom is at the end.
Yeah, so do you have to do it for every atom, right?
Oh yeah, you can do it with all atoms in parallel, but it's not like ions where they're interacting so that there are tons of different modes that you have to cool at the same time.
Okay.
It's just a product state of motional states, so you don't need it.
Okay, thank you.
So additionally, this ground state can have nuclear spin, and you can use that to store quantum information in a different way from, say, this clock transition, which is actually quite useful. I won't talk about it in my talk, but I just sort of wanted to highlight this. Okay, so as advertised, these different transitions have resulted in a lot of activity in the past 3 years or so, ranging from new trapping, cooling, and detection techniques for cold atoms and tweezers, this idea of a new clock architecture that'll be the focus of this talk, and furthermore, and I'll briefly touch on this at the end, using new ideas for engineering entanglement in these systems using Rydberg interactions. Okay, so over the next bit of time, I'm really going to try to give you a whirlwind tour of the technology in our lab. I'll then describe our tweezer clock studies over the past 1.5 years. And then I'm going to tell you about very recent work we've been doing for engineering entanglement in an optical clock. Going a little bit slowly here, so I might rush through some parts so I can get to other parts. Okay, so our experiments, both schematically and photographically, if that's a word, look like this. So the important features of the experiment, we have this microscope that I was showing you earlier. We have this plate here, which allows us to co-register in space optics that need to be phase stable with the microscope itself. And then we have a vacuum chamber that you can see here in which the atoms live. So the vacuum within that cell there is 10 to the minus 12 torr, which for reference means that an atom that's in there will not collide with any sort of background particle that's uncontrolled for hundreds of seconds. So this really means that we can have these really pristine isolated systems that are not perturbed by aspects of the environment. So importantly, we can make a cold cloud of atoms. That's that blue dot there inside of the cell. So you're now looking at the cell from over here. And from that cold cloud, we can load individual atoms. So these are images from our actual experiment. So this is an average image. And a single image looks like this. And what this is showing you is that we actually load atoms stochastically into the trap. That is, there's a 50% probability that any of the tweezers might have an atom. For much of what I'll be talking about today, that actually ends up being irrelevant. But as I was showing you in earlier slides, there are ways of rearranging the atoms so that you can have defect-free samples. Good. Okay, so this overall technology sounds sort of simple. I have a laser, I have a microscope, but in fact, they've gotten really complicated. So we have two optical tables that are basically like completely full of optics. So this is our so-called laser table where we make all the lasers that get piped over on optical fiber to this table over here, which is our science table. And then right in the center there is the vacuum chamber, which you can't really see because of the coil structure around it. An important aspect of these systems is the fact that the tweezers themselves can be very tunable in space. So in our lab, we use Acousto optic deflectors, which are devices where if you apply an RF signal, radio frequency signal to the device, it makes a small standing wave, which allows you to diffract the light at a particular angle, dependent on the RF frequency that you put into the AOD. So this gives you control over the angle of the light that goes through the Acousto optic deflector. And we have two of these to do deflections along two orthogonal axes. And importantly, if you put a beam that's at an angle into a microscope, it changes the position of the focus spot. So by having a comb of frequencies that come out of this, or comb of angles of beams that come out of this AOD, you can make an array of spots like this shown here. And we've spent a lot of time developing electronics for really being able to control these well. Good. Another technology that we use in the lab as well is so-called spatial light modulation. So we use, and I'll call this an SLM. And the idea here is that by controlling the phase of the wavefront in a two-dimensional way, you can control exactly the distribution of the spots that you'll get after a microscope. The key thing is that this microscope actually takes the Fourier transform of the light that diffracts off this SLM. So this gives you much more arbitrary control of the light that the atom sees in the chamber. So for instance, you can make triangular arrays, Kagame lattices, a JILA lattice if you were interested in doing so. And you can even do three-dimensional things. So this is a video here where we go from, we're scanning in the Z direction of our optical system, and you can see that it comes to a focus in two places, which means you could say engineer arrays of atoms that are coupled in a 2D layer configuration. And this is important because all of this is important because it really means that you can use these well-established techniques for optical engineering and turn it into really being able to engineer the environment of the atoms themselves. Okay, so once we have atoms trapped in our tweezer, we do a combination of scattering off this imaging transition and cooling at the same time to make up for the fact that this scattering actually heats the atoms a little bit. And this actually was pretty tricky to get working, but it now works quite nicely. So that in 18 milliseconds, we can collect enough photons to know whether or not there's an atom in our trap. So this is when we don't have an atom, and this is when we have an atom. And that process can have less than 0.1% loss. That is, the atom heats out of the trap or disappears for some reason less than 1 in 1,000 times. And furthermore, we can distinguish these peaks at the 99.9% level. So this degree of high fidelity is really important for a lot of these studies. Importantly, and this gets to Jeshuan's question, we can also do ground state cooling in these systems. So I'm showing here a so-called sidebound spectra. And the key thing to take away from this is the following. So on the right here corresponds to a transition where we go from this electronic ground state of single S0 to triplet P1, while at the same time adding a quantum of motion to the atom in the trap. So we can actually resolve different motional states in the trap. So that's what this peak corresponds to, is when we're tuned to a transition that adds a quantum of motion. On the left here is where there would be a transition for removing a quantum of motion. But when the atom is in the ground state, that transition does not exist because there's no lower energy that it can go to. Hence, this asymmetry allows us to extract the temperature of the atom. And in this case, we can do this in all three directions. And we can see that we have an 80% three-dimensional ground state fraction in 20 milliseconds. Okay, so that's sort of a brief overview of the technology here. If there are questions about that, I can quickly take them. Otherwise, I'll move on because that was deliberately a bit fast. Okay, I will keep going then. Good. So a natural question I ask is why make a tweet? Like, why would anyone want to make a tweezer clock or make some sort of technology for metrology based on tweezers? And answering that question really goes back to answering sort of what an atomic clock is, which frankly, before I began a lot of this research, I was not that familiar. So I would imagine that not everyone here is also that familiar. So an atomic clock works like any clock. It uses the periodic regular behavior of some object to track the passage of time. So for instance, if a pendulum is swinging, I can count how many times it's gone through its periodic behavior to know, say, if 10 seconds have passed. That's how you might keep track of time. But the key is having some periodic behavior that's well controlled. So in an atomic clock, that periodic behavior can be viewed in a couple different ways. So one is the way that I was talking about earlier. If I put an atom in a superposition of a ground state and an excited state, there is an oscillating dipole in the atom corresponding to the electron jiggling back and forth at the frequency that separates these two levels. Another way of thinking about it, which is the more quantum mechanical picture, is that I can think of this spin as existing on the so-called Bloch sphere, just the representation of a two-level SU2 system. And in the equatorial plane, the atomic coherence, that is the relative phase between the ground and the excited state, is whipping around at the energy difference between the ground state and the excited state. And so that's the periodic behavior that you might imagine for a quantum mechanical perspective. And importantly, the lifetime of this superposition is really upper bounded by the lifetime of this excited state. And thereby, it also upper bounds the quality factor of the oscillator. So the fact that this can be very long-lived and these frequencies can be so high means the quality factors can be exceptionally large and allow amazing degrees of precision and accuracy. So just as an example, this is a plot that's actually now somewhat out of date that shows the fractional frequency uncertainty, that is how well you can know the frequency of this transition in the clock, and thereby how well you could track the passage of time using this system. So this shows the progress in that fractional uncertainty as a function of time that these systems have been studied for. And you can see that in recent years, we're at the point where we have 10 to the minus 18 or 10 to the minus 19 accuracy in trapped ion and neutral atom clocks. And furthermore, one can acquire precision with just an hour of averaging time. So this means you can measure things like gravitational redshifts over a centimeter distance. You can use these clocks for things like geodesy, for navigation and timekeeping, and of course for more timekeeping applications like redefinition of the second, or even more fundamental physics applications like looking at the time variation of fundamental constants. So this has been a very fruitful area. To really dive into the details of how these clocks work, I'm going to focus in on so-called optical clocks, which rely on a laser, which is driving the transition in the atom. There are different kinds of clocks. You can use a microwave clock, which drives a microwave transition, or an optical clock. That's what these red and blue correspond to here. So in the optical case, you have this laser, as I was saying. And typically the way this works is this laser is locked to a reference cavity. And this cavity can take care of a lot of different noise, except it's really sensitive to things like thermal fluctuations of the environment, which cause this solid state object to slowly drift in time. So we need some absolute reference for the lasers that it stays at a particular frequency, and that's where the atoms come in. So the stability, which is the precision that this clock can accrue as a function of averaging time, depends on the quality factor of the transition, as well as the number of atoms that the sample has. The first thing, this quality factor, you can think of this, and I've brought this up a few times now, you can think of this as basically, for my temporal ruler, the Q is the number of ticks on my ruler. So this is really telling me how precisely I can track time and for how long. The number of atoms is important because this system is limited by so-called quantum projection noise, which is actually just a very simple thing. I have a bunch of atoms, but they're only, when I measure them, they're only sometimes up or sometimes down. They're never in between up and down. And that gives rise to fundamental noise, which averages down more quickly if I have more atoms to sample in parallel. This is exactly identical to flipping coins. If I have 10 coins, the fractional fluctuations about 5 are larger compared to the fractional fluctuations about, say, 500 if I have 1,000 coins. Another important effect that influences the performance of clocks, in addition to Q and having many atoms, is an effect known as the Dick effect. And I'm not going to actually say too much about this, but it's important to highlight. And it's this idea that the laser might have some high frequency noise on it that you're only stroboscopically sampling when you compare the laser to the atoms. And this gives rise to a form of noise known as Dick effect noise, which actually compromises the fundamental stability that you might think is possible with this system. So all in all, what this means is that our wish list for making a really good clock is having many atoms, having a long coherence time, and we want a long coherence time because that sets the line width of the transition that we can probe, and thereby the quality factor of the oscillator that we're sampling. And furthermore, have a high duty cycle to reject these effects that I was just describing at the end. So the leading platforms for this have been trapped ions, where single ions are trapped electromagnetically. And these systems are amazing because you have a single idealized quantum sensor that can be probed at very high duty cycle. The problem is that you have a single ion, so you're really limited by this quantum projection noise that I was describing. On the other hand, there are optical lattice clocks, which have many, many atoms, up to sort of thousands of atoms. But because you have a lot of atoms at high density, they can collide with each other. They can also move around in the standing wave potential that traps them. And this can give rise to problems in the accuracy and coherence time of the clock. Furthermore, the duty cycle that you can sample these systems can sometimes be a fair bit lower than what's possible in trapped ions. So now let's think about the capabilities that I was describing earlier in the talk. So the first is that we can have more than one atom. We can have, in this picture here, 10 atoms. And as I showed you earlier, we can actually have a lot more than that, more like 160. And we can load those atoms pretty quickly in about 100 milliseconds. It's actually now a fair bit faster. We can image these atoms at high fidelity very quickly. We further can cool these atoms to the ground state quickly, which is actually important because the temperature of the atoms influences the amount of time that we can coherently probe them for. So being cold means you have a longer coherence time. And when I combine all of these different things that we have to do in the experiment, we can do it in under 200 milliseconds, which in practice means that we can have a very high duty cycle clock based in this use of tweezers. So implicitly, these experiments are asking the question of whether in between these two leading platforms of trapped ions and optical lattice clocks, is there room for this new kind of technology that allows for a single particle isolation, long interrogation times, and intermediate atom number, in the sense that it's more than what you have in trapped ion systems, but typically less than what you have in an optical lattice clock system. So in our first work exploring this, we were able to really use this amazing laser technology in the Yi group, where you can have under 10 millihertz wide lasers to probe the coherence time of the atoms. And we can do this in a novel way where we load the atoms, we perform clock spectroscopy and interrogate this transition, and then we image again at the end. And by doing that, we can tell how many atoms were transferred to this excited state here. So importantly, we observed that the atom laser coherence time, that is how long the oscillating atomic coherence at an optical frequency stays in phase with the laser that drives the atom, that can exist for 3 seconds, or a little bit more than 3 seconds. These experiments can operate at very high duty cycles. So because we have this long coherence time and a short dead time, the duty cycles can be up to 96%, meaning that only 4% of the time are we not actually interrogating the clock transition. And we can do this repeatedly so that we can have 20 seconds of near continuous interrogation of the atoms. Furthermore, the stability, that is the precision that we can accrue as a function of time, was pretty good. It wasn't the state of the art or close to the state of the art at the time. It was about a factor of 10 off. And that was really limited here by the fact that to have these long coherence times, we really had to operate with a smaller number of tweezers so that our ground state cooling would work. I can answer questions about that if you're interested, but it was a really key trade-off. Importantly, around the time of this work, there was another beautiful paper from the Caltech group that showed having 40 atoms in tweezers. So that's more than what we had in this work here, but at much shorter interrogation times. So it's really showing that while the achievable, it shows this fact the achievable coherence time is really influenced by the number of atoms that you can have, because it sets sort of how well you can control your system. So this really made us think, how large a system can we scale to while maintaining quantum coherence? So this motivated a revamp of our setup where we added a fair bit more complexity. I won't say too much about this, but basically we use multiple different tweezer arrays, which are all co-registered in space, in addition to a standing wave optical potential that allows us to squish the confinement along one direction of our trap that's more weak. And altogether, this allows us to have loading, ground state cooling, and good control of the clock transition for actually 320 site systems. Maybe I'll skip that. So good, okay. So importantly, when we do this kind of scheme where we use 2 colors of tweezers, what we found is that for the whole array, we have very long lifetime. So I'm showing here a plot that shows as a function of trap depth, the lifetime of the ground state in black. And so you can see that for really low trap depths, we start to lose the atoms somewhat more quickly, and the lifetime really goes way down, which is up on this axis here. And for the excited state, we see a similar behavior where the lifetime drops as you go to lower trap depth, and a similar behavior at higher trap depths. And this has to do with a Raman scattering decoherence mechanism, which is well known for these traps. But the key thing is that at this minima here, we have an excited state lifetime that in practice, without any sort of post-selection or anything like that, is about a minute long. And so this really sets the timescale over which you can coherently interrogate the system, which is exactly what we next set out to do. So to understand how coherent a system is, or a qubit is, one typically does a so-called Ramsey experiment. That is, you apply a pi/2 pulse to some qubit. In this case, it's at the clock, the transition, the 2-level system is on the clock transition. You allow that the qubit to acquire a relative phase with respect to the drive that drives the qubit. And then you read out that relative phase with a second pi/2 pulse, which maps the phase onto a relative inversion of up and down. And importantly, for these experiments, we can do this. We don't need to take many runs to figure out the relative phase. Just one is sufficient. And this is sort of a subtle point, but it's actually important for the measurements that I'll show. So this is showing the measured excited state fraction, that is the measured triple P0 fraction, as a function of Ramsey dark time. That is the amount of time that the atoms sit accruing a relative phase. And what you can see here is that the atoms, their average value shows large fluctuations, which follow this dark gray envelope here, this, or sort of medium gray dark envelope here. And so what are these envelopes? So this first one here is the expected loss of coherence from an atom loss from the trap and a decay from the excited state. This medium gray, this corresponds to both these effects here from the light curve and a known dephasing mechanism that we know that arises in these systems. And this darkest gray, this is actually the dephasing that we independently measure between the atoms and the laser. So what does this really mean in practice? So if you blow up these different sequences here, you can see that at short times below 3 seconds, there is a well-defined fringe in the Ramsey data, and that's just because there's a well-defined phase between the atomic ensemble and the laser that drives the atoms. That is to say, there is atom-laser coherence, that coherence here meaning there's a well-defined relative phase, but there's also atom-atom coherence. That is to say, different qubits in the ensemble have the same relative phase with respect to each other. If they didn't, then they wouldn't respond to the laser in the same way, and we wouldn't see this fringe. At times of about 20 seconds, the fringe is gone, but there are large fluctuations still persistent in the sample. And what's happening here is that the relative phase between the laser and the atoms has now been lost. And so we're just randomly sampling this fringe that we see at short times. But the fact that there's still atom-atom coherence means all of these atoms are responding the same way to the laser. And at really late times, both these forms of coherence are gone. So at these intermediate times here, what this is really saying is that there's correlations in the direction of the block vectors for the individual atoms in the array. So we can actually use the site-resolved readout that we have in this sample to look at something known as the G2 correlator. The G2 correlator is just the likelihood that two atoms separated by a given distance are pointing in the same direction at the end of the experiment. And importantly, in this Ramsey sequence, at the end of the Ramsey sequence, there's an enhanced likelihood of these correlations when there's atomic coherence still in the ensemble. More specifically, this G2 correlator is proportional to the off-diagonal matrix elements of the single particle density matrices. And what we see is that at times of 1 second, there's very strong homogeneous correlations. And then at later times of about 25 seconds, there's still in this on diagonal of the tweezer array, there's still well-defined correlations that are positive. But then on these opposite corners here, there's actually anti-correlation. And this comes about because of this dephasing mechanism that I've alluded to a couple times that arises in these tweezer systems. And we can actually model this behavior here and see good agreement qualitatively between where these regions of positive and negative correlation arise. Okay, so the upshot of all of this is that we can actually use a combination of Ramsey measurements and these correlation measurements to benchmark that the ensemble atomic coherence, that is how long the ensemble can store a well-defined phase, is about 20 seconds, 19.5 seconds. And the single particle coherence, which is not limited by this dephasing mechanism, that can be about 50 seconds long. So all in all, the atoms have an intrinsic quality factor of 6.5 times 10 to the 16. That is, these systems can ring this many times before the oscillations damp out. And so this is actually really a record for basically any system in nature. So using this long coherence time, we can do something known as an Allen deviation test. This is not critical to understand exactly what this is, but the key point is that you can measure the relative frequency between one side of the ensemble and another side of the ensemble to get a sense of how stable the whole system is. And importantly, what we find is that the precision that we can measure this frequency averages down like 5.2 times 10 to the minus 17 per root tau, that is per root second that we average for. And at 10,000 seconds, we have a relative precision, that is the precision which we can measure the frequency of this side of the sample compared to this side of 4.2 times 10 to the minus 19. So this is actually on par with the state of the art for lattice clock systems. So the system is really now, even though it's somewhat new, is becoming competitive with the leading clock systems. Looks like there's a question, Jeshwan.
No, it's just a comment. The numbers are very convincing.
Convincing. Okay, so actually that's, we're good, I'm on time here. So I'm going to transition here to the last part of my talk. Are there any questions about the clock section? Okay. I was recommended when I started teaching that I should wait always 7 seconds whenever I ask their questions. And I think that was about 7 seconds plus what I just spent talking. Okay, so I'm going to tell you now about recent efforts going on in our lab. So there's this really important idea in metrology, which is that the performance of a clock can be enhanced when it has entanglement. In the beginning of the talk, I talked about different ways that these tweezer systems can be used to engineer entanglement. So that means that this technology is really well poised to make an entangled clock. That is, I just showed you that we have this stable, long-lived clock, and there's been this beautiful work out of the Lucan group at Harvard, where they can show things like not long-lived actually, but large cat states, that is, superpositions of all of the atoms being one state or all of the atoms being in another state. So this really gives rise to this idea that you can have a long-lived, well-controlled, entangled optical clock. And I'm going to use the method by which we want to do this to explain how you can actually get enhancements in a clock system. So I'll sort of explain things as I go along here. So the kind of interaction that we want to use to make entangled states is using so-called Rydberg interactions. And the key idea here is that if I excite an atom to a very highly excited state, known as a Rydberg state, the electron orbits of the excited electron are very fluffy. So if I have two atoms in Rydberg states, I have two fluffy electron orbits that are proximate to each other, and they can exhibit dipole-dipole interactions. That is, the electron of one atom can induce a dipole in the electron orbit of the other atom. And so what this does is it gives rise to actually huge energy scales, interactions between the atoms of around 100 megahertz over micron spatial scales. And that's exactly the sort of spatial scale that we typically separate our atoms in the experiment. And the particular thing that we like to do in our lab is so-called Rydberg dressing, which is the idea that instead of having the Rydberg the Rydberg state populated resonantly, that is, you transfer excited state population to the Rydberg state, we sort of do it off resonantly. And what that does is it causes this excited state of the clock transition to perturbatively inherit a little bit of Rydberg character. So while you might not have the 100 megahertz energy scales that are intrinsically possible with these Rydberg states, you can have kilohertz energy scales, which is more than enough for the kinds of physics that we want to look at. And this too can occur over 1 to 3 micron spatial scales. And so what this means in practice is that if I have two atoms near each other, if those two atoms are both in this excited clock state, then there's an energy cost associated with that. And a system where you have an energy cost that depends on the spin of the atom, there are different kinds of ways this can be manifest, but one kind of model is a so-called Ising model, and that's exactly what we're producing here. And importantly, this Ising interaction can realize so-called squeezing, and this is where the metrological gains are possible. So if I have an ensemble of spins, I can represent that ensemble on the block sphere with a distribution like this. So if you're familiar with, say, phase space representations of harmonic oscillators, you can think of that as the same thing here, where I just have a Gaussian distribution of the noise associated with the spin. And the degree to which I can measure a phase precisely in this system, which is what I want to do in an atomic clock, really depends on the size of this distribution. Now, these Ising interactions do something very important. What they do is they realize a rotation of the block sphere, which depends on the value of the spin. That is, if you're a little bit above the equator of the block sphere, the system precesses this way. Or if you're a little bit below the equator of the block sphere, it precesses this way. And what that means is it shears this noise distribution so that along one axis, there's a lot of enhanced noise, but then along another axis, there's actually reduced noise. And if we do phase measurements along this axis along which there's a reduced noise, we can actually have quantum enhanced phase measurements. And that's only possible when we're able to engineer entanglement via things like this Ising Hamiltonian here. So there are a couple different ways of doing this, but one idea that we've been really keen on is this notion of optimizing the amount of squeezing that's present in the system by doing a combination of global rotations on the clock transition staggered with these periods of Ising interactions. And what's nice is that you can stack up many of these layers and optimize the time that you interact for and the angle that you rotate by to get more and more squeezing. So for instance here, if I go from this blue line here down to this orange line here, what I'm doing is adding more and more squeezing. This C squared here is the ratio is the log of the ratio of the noise along this direction to this direction. So when it's really negative, that means you have really reduced noise along this axis. So you can see that the squeezing is getting better and better as I add more and more of these gates. And furthermore, it gets better as the range of the interactions, this RC over A, gets larger. So we're sort of keen to try to kind of like get to all of these different things. So to really do that, in this last bit of my talk, I'm going to talk about some really preliminary data from our group. This is sort of really from the past 3 months. It looks like there was a question, Joshua. Should I answer that before?
Actually, I didn't see the question. Is that in the chat box?
I thought I saw the thing flash. Okay, never mind.
Yeah, but you got a couple minutes more, and then the students will have the time to ask all questions.
Okay, sounds good. So to really get this kind of sequence going, and even to perform this kind of squeezing protocol, we need to have 2-qubit control. That is a way of engineering interactions in the system. That is through coherent Rydberg excitation. And we further need to have much higher fidelity qubit control of the clock transition. So I showed you earlier spectra where the contrast of the oscillations was only about 80%. This first bit of having a coherent Rydberg excitation, we've made a lot of progress in. This is a fairly complicated laser system that we developed in collaboration with friends at NIST. And we can have nice coherent control of the Rydberg transition and at a very high Rabi frequency of actually 20 megahertz. And this is over a large spatial scale of about 35 microns, which is commensurate with the tweezer arrays that I was showing you earlier that had 160 atoms in them. And I want to highlight too that this isn't the focus of this talk, but the Caltech group has actually been able to use this kind of protocol to do 2-qubit entanglement on the Rydberg transition at the 99.5% level. So this is a really nice transition for doing coherent operations on the atoms. So the 2-qubit part is, we got that figured out. The next part is we have to have really good control of the clock transition. The way we're doing this, and this is a little bit technical, but I wanted to come back to it, is we actually overlap in space with our microscope a standing wave optical potential, and it's an optical lattice. And what's key is that the optics that make this lattice sit on the same plate that holds our microscope. So that ensures that all of these things are moving in parallel so that we can really deterministically load atoms into individual sites of the lattice. And importantly, we can also ground state the cooled atoms into this lattice. Good. So the reason that this works, that this helps our clock physics, is that the tweezers can't hold on tightly enough to the atom to avoid various infidelities that arise in these experiments. But by using the lattice, we can actually have 99% or more control of the clock transition and the fidelity with which you can rotate the atoms. And this light gray here is actually the data that I was showing you earlier. The best we saw was about 87%. So we can do these clock rotations at very high contrast, and also for other technical reasons, we can do them a lot faster. The other thing is that we can do single atom site resolved imaging of the atoms in this standing wave lattice. So here are single in lattice images. If we make a histogram like the one I was showing you earlier, we can have 99% fidelity of detecting whether or not we have an atom, and the atoms remain at that same site during the imaging. They aren't flying away. Importantly, even though we're imaging the atoms in the lattice, which is this square grid, which sort of sounds like you're sacrificing on some of the tunability that you have in tweezers, where you can just like move the atoms around willy-nilly. As long as the underlying spacing of the lattice is small compared to the spatial scales that you care about, you can still do that. So for instance, we can rearrange the atoms to be loaded into the lattice into doublets, so that we have arrays of doublets here. And actually, this is exactly what we've been doing most recently, because we've been trying to create entangled, 2-qubit entangled states on the clock transition. And this is very recent data that we've just started to get working, where we use this, this model got a little bit cut off, I apologize. We use this Ising interaction from the Rydberg Dressing to create bell pairs of a superposition of GG plus EE. And by varying the angle, the relative phase between these two components, we can realize so-called parity oscillations. These parity oscillations are just the likelihood that the atoms respond the same way or the opposite way to a pi/2 pulse. That's what parity means. It's a witness used to benchmark how much entanglement is present in the system. So this is by no means a record for entanglement in a qubit, but it's the first time that in a tweezer system one has done this in an optical clock. And it actually is the first time it's been done for a cat state on an optical clock. So this is really exciting because you can begin to think about using the increased phase sensitivity of a Bell state to perform improved metrology measurements. Okay, so that brings me to the end of my talk here. So there's really a lot to do with these systems. So I told you about this metrology direction and trying to use entanglement to enhance the performance of a metrological sequence. I didn't talk about this, but another thing that my lab really focuses on is trying to do quantum many-body physics and simulation in these systems. And one thing that's quite cool that we've been playing with now is that now that we can load individual atoms into a lattice, we can actually look at Hubbard physics in that system. So these are pictures here of an atom undergoing a two-dimensional quantum walk. And this is an averaged image. On any run of the experiment, we'd see the atom in one place. But when we average, we see this interference pattern, which arises because there are different paths that coherently, constructively, and destructively interfere as the atom quantum walks in this underlying lattice potential. And finally, another direction we're interested in, which is very related to these 2-qubit demonstrations that I was just describing, is doing quantum information with these systems. And to that end, I actually have a new experiment that we're developing, which focuses on using a different atom known as ytterbium, and in particular, trying to get control of this nuclear spin that I talked about in the beginning of my talk. Okay, with that, I will conclude here and just bring back up a lot of the people involved here who really have been pushing this along. Thank you.
Thanks a lot. This is a fantastic talk. So let's now open the stage for questions. So if you have any questions, you can just unmute yourself and ask Adam.
Hi, Adam. Great talk. This is Nick. I asked the question earlier about the duty cycle.
Yeah.
And you guessed it. I work in superconducting qubits. So
yeah, I mean, it's not even close to a superconducting qubit system, of course.
Yeah. I was curious. So you were talking about CAD states. Have you looked into noon states? Who are these other kind of more than bell pair kind of entangled states?
Yeah. So when that Ising interaction is symmetric among all the atoms, that is to say the magnitude of the interaction is the same between any pair of qubits, then you can use that to create larger entangled states beyond just 2. You can make an n particle entangled state where n is the number of atoms that you have that are all interacting symmetrically with the Ising interaction.
And I guess maybe the reason I ask about noon states is, generating bright entangled states of light is still an open question. So how does this system relate to that? Is there some sort of comparison?
Comparison in the sense of like, can I map a spin cat state onto a noon state of light? So is that the question?
Yeah, I guess you answered the question then. Yeah, you can.
Yeah, well, no. That hasn't been done before, but I think that's the kind of thing that one might be able to do. Yeah. I'd have to think a little bit more about it, but it doesn't seem impossible. I think it would involve the use of an optical cavity where all the atoms are, in principle, interacting with a common mode of the electromagnetic field within the cavity.
Great, thank you.
Any other questions?
Hi, Adam. I had a question. Maybe I missed it, but When you're loading these atoms, do you put them in the Rydberg state first and then put them into the trap, or do you get them into their sites and then excite them?
Exactly. Yeah, it's the latter. So you load the individual atoms. They're sort of naturally in the ground state anyway, just for thermal equilibrium reasons, and then you can excite them using these UV lasers.
Right. Okay. And so the force that holds them in, that keeps them in the trap, isn't affected by the fact that they're in those states. I mean, there's the attraction between them.
That's a really good question. So so the way these light traps work is, so if I have a 2-level system, for instance, and I park a laser below red of the transition, then that pushes the energy of the ground state down. So if I have a spatially varying light field, then that makes a trap because the internal states of the atom shift down in energy in a position-dependent way.
Right.
Of course, an atom is much more complicated than a 2-level system. So different states in the atom will interact with that light differently. So in an alkali atom, the Rydberg state is actually anti-trapped by the light. It wants to move away from it. But in alkaline-earth, it's a little bit more subtle. Is this answering your question?
Yeah, what you're getting there. I mean, I'm just trying to, because normally you have, like you said, you have a certain transition that you're using to have the force, but then you've gone and put it in the Rydberg state, and so.
Yeah. So there are two things. So one, for the Rabi oscillations that I was showing, those are occurring in under a microsecond, even though the trap period here is about 30 microseconds. So this is all happening super fast compared to motional timescales. So none of that ends up mattering on that timescale.
Mm-hmm.
That's the first thing.
Mm-hmm.
The second thing, which is a lot more subtle, is that for the Rydberg dressing, what's happening is they'll actually still debate it a little bit, I should say. But the key point is I'm only coherently putting in a little bit of quantum amplitude in the Rydberg state. So that portion of the wave function is indeed, for a longer period of time than the trap frequency, sampling the optical tweezer potential. Mm-hmm. And that can actually influence things like interactions and stuff like that. Mm-hmm. The subtlety here is that you actually, what I just said is a slightly oversimplifying it, because in fact what happens is you need to take into account the full dressed state picture for what the trapping potential looks like, which actually changes things a fair bit, so that the atom can live a fair bit longer than the time scales of the trap itself. Mm-hmm. So it's a little odd, but it's actually also one of the reasons why we wanted to do this dressing scheme rather than the resonance scheme, because we didn't want to have to worry about trapping issues.
Right, right. Okay, thanks.
Uh-huh.
Okay, we have time for 1 or 2 more questions.
Yeah, I have one. It may not be too bright. You had a plot of the probability of your atoms escaping the trap as a function of the depth of the trap for the ground state. And it seemed to flatten out as the depth of the trap.
Yeah, I meant to say something about that, and I was going too fast and didn't. So what's happening there is that there's a fundamental time scale which is set by the vacuum lifetime, which was 160 seconds for those experiments. So when we go to the deepest traps, we're not limited by the technical noise that we have in the experiment that heats the atom when it's at shallow traps. The basic idea is that there's some acoustic noise in the experiment from stuff shaking. And when your trap frequency becomes comparable to those mechanical timescales, then you can resonantly shake the atom out of the trap, which is bad. So if you make the trap deeper, that means that one, those trap frequencies are moved to higher frequencies, so you're outside of this acoustic band. And two, you can suffer a bit more heating before losing the atom. So that's why the timescale gets much better as you get to deeper traps.
Thanks.
Mm-hmm.
All right, maybe the last question. All right, maybe I can ask a question here. So, so this is more for quantum simulation, or this quantum antibody physics. So when you are using Rydberg dressing, then you also have to worry about these Rydberg states decay to other states, right? Maybe some p states. That's going to make your coherence time quite limited. I'm not sure, how good is the coherence time at this moment. Have people sort of solved this problem partially, or can actually see many cycles of exchange interactions?
Yeah, this is an interesting question and has been somewhat of an experimental debate. And I think the debate is actually just that different systems seem to suffer more or less with respect to this problem. So we actually have lifetimes of the Rydberg dressed atoms that are really, really long, like longer than we thought they should be based on our measurements of the Rydberg state lifetime. Which is probably because our measurements of the Rydberg state lifetime were artificially shorter than they actually are because of these anti-trapping effects that I was just discussing with Chip. So we don't see these sort of catastrophic loss mechanisms that people have seen. And I think a key reason why that might be is that we control the density so well. Like we only have as many atoms as are there. It's not like there's like a really high density of like 100 or 1,000 atoms. And it's when you're in that case that you're really in trouble, because if you have just one atom that decays to a p state, everyone is unhappy.
So then your system can be used for quantum simulation.
Yeah, I mean, we can do both the resonant Rydberg and the dressing case, right? So even if the dressing case ends up being a scaling problem when we get to a certain size, then there are alternatives. But yeah, I do think that. And also I should say too, like there's this beautiful paper from the Bacher group at Princeton where they do Rydberg dressing in lithium. And there they have not only long-lived Rydberg dressing, but also itinerance. That is, the atoms can tunnel around on the timescale of spin interactions. So you can really start thinking about doing quantum simulation of itinerant spin models. It's really new.
Yeah, if there are no other questions, let's thank Adam again for the wonderful talk. Yeah, have a good one, everyone.
Thanks a lot for the invitation, Joshua.
Thank you.
All right, so we'll be talking tomorrow.
Yeah, we'll be talking tomorrow. Yeah.
Cool.
Yeah,
All right.
thanks a lot. Yeah.
All right.
All right, see you then. Yeah, bye.
Yeah.